Good afternoon, everyone. I extend my welcome to all of you here, and I am quite sure that we would like to have this session very interactive, in which we will have first lecture by Professor Sumanta Haldar, followed by the technical presentations. And sir, 15 minutes would be sufficient for you? So 15 minutes will be there for the lecture, and subsequently every presenter will have 9 minutes to present, and thereafter we'll have 2 minutes for question and answers, please. Right? I'd like you to ask as many questions and answers as possible, and let this be an interactive section. So with that, I welcome Professor Halder, and I'd like to have a few words about sir. Dr. Halder is a professor of civil engineering and presently head of School of Infrastructure at IIT Bhubaneswar. He earned his PhD from Indian Institute of Sciences, Bangalore, and he specialized in geotechnical engineering with core expertise in offshore geotechnics, soil structure interaction, dynamics of load and foundation, and reliability-based design. With over 15 years of academic and research experience, he blends theoretical modeling with computational and experimental methods. A recipient of Professor Leonard's Best PhD Thesis Award, he has published widely in reputed journals. Dr. Halder leads several sponsored research projects and significantly contributes to infrastructure development, promoting sustainable and resilient solutions for energy and civil engineering applications. And then I'll welcome our co-chair. So we too will be taking care of you here. So over to you, sir, please.
Thank you.
Thank you, sir. Pleasure.
Yeah, thank you, Mr. Chairman, for a nice introduction. So first of all, I'd like to thank all the organizer, the team Geotech Asia and organizing committee for giving me the opportunity. So today I will talk about the numerical simulation of floating offshore wind turbines under environmental and seismic loading. So basically, the topic of this particular presentation, the contents are given here. So I'll first briefly talk about what is offshore renewable energy structures and what are the typical foundations that we generally adopt for different type of structures, and what are the current development across the globe and as well as in India. So I'll mostly talk about the preliminary assessment, the preliminary simulation methods, like how do we simulate the particular structure using numerical methods, and some kind of validation or the verification of the developed model that I'll be talking about, and some responses, the preliminary assessment that we have done. It is basically the work of my PhD scholar, Ms. Maria James. So the offshore renewable energy structures, if you look at the different type of structures, it is very much promising because as per the global energy demand in the current date, we are expanding, basically the world is expanding towards the sustainable and green energy. So these are the typical, so offshore wind energy is another one most promising method to explore the wind energy, explore the green energy. So we mostly have two different type of structures. One is a grounded structure or the bottom fixed structures, and another one is a floating structure. So grounded or bottom fixed structures are generally deployed at shallow water depth, maybe up to 30 meter or 40 meter water depth. But if you are trying to explore at the deep offshore, deep ocean, the floating offshore wind turbines are most promising and more economical, because at beyond 50 meter water depth, sea water depth, the grounded structures may not be feasible and it will be very expensive. So, and also in the deep sea, it is away from the coastline, the state of the sea is also calm, because as you go towards the coastline, the sea will be more turbulent and non-linear waves will come into picture. So there is a promising or the challenging, like the design of such kind of structure is more challenging, and many countries they are adopting currently. And why the floating offshore wind is important, because India has, and in terms of the Indian scenario also, it is very much like it is possible. So far, of course, we do not have any kind of offshore wind energy explored by the Indian government, but we have been trying to explore, because already the feasibility studies have been done. So based on the feasibility study, it has been seen that there's a potential of 112 gigawatt of bottom fixed and 83 gigawatt of floating offshore wind potential, mostly in Gujarat, Maharashtra, Kerala, and Tamil Nadu. And the countries with deep continental shelves, like I'll talk about what is continental shelf and why it is important. Mostly in Japan, Scotland, and the US west coast, you may find the continental shelf is very narrow, and the deep water comes very early from the coastline. So there is a significant capacity of offshore wind farm in terms of the floating system. And why floating offshore wind? Because it can produce more energy as compared to the bottom fix. So first we'll look into the different type of foundations of offshore wind turbines. We can have mostly grounded system and the floating system. And these are the support structures, mostly monopile jacket structure and some other different type of structures. And floating system, mostly we are exploring three different type of foundation, three different type of floating system. One is the tension leg platform, semi-submersible, and spar buoy. And I will discuss mostly on these three different type of structures and their numerical modeling. So these are the typical, the schematics diagram of three different type of structure. TLPs are basically the floaters are connected with the tension leg. These are basically tendons. The tendons are connected with those floaters. Spar buoy systems are basically the buoyancy stabilized system. It's a single column structure. And mostly it is deployed in deep water, maybe more than 100 meter water depth. And these are the semi-submersible system, which are mostly balanced by the area. That means the moment of inertia, which is produced by the water plane. And this type of structure, semi-submersible structure, are also possible in case of medium depth water, maybe 50 meter to 100 meter. So it can be deployed for different type of water depth. But mostly the TLPs are deployed in shallow water depth, but the spar buoy concept is used for deep water. So these are the scenario, the current scenario. If you see the Europe, the present scenario of the floating offshore. So Norway, Portugal, Aberdeen, France, they have already explored quite a lot of offshore floating offshore wind energy foundation. In fact, I have a opportunity to visit the France offshore, and where they are basically deploying those kind of structures. So this is one of them. This is the structure which we visited in France offshore. And if you look at the other Asian countries, the China and Japan, they have already developed those kind of structures, and they are exploring the wind energy through the floating system. So this is one semi-submersible structure. This is a spar buoy structure, which is deployed already in Japan, and the high wind turbine system. So if you look at the current LCO, there is a levelized cost of energy across the globe. And you can see the cost is very high with the red zone, and the cost is less at the blue zone. And if you look at the scenario in terms of the Indian perspective, across along the Gujarat coastline and the Kerala and the Maharashtra, the cost is a little bit higher on the higher side, but at the Tamil Nadu coast, it is on the lower side. So there is of course, there is a possibility of like deploying such kind of system in our offshore area. So if you look at the continental shelf of India, the west coast at the Bombay High, the continental shelf is quite wide, but at the east coast it is very narrow, like 30 kilometer in Madras and Vizag. So the deep water is coming very early. It's very close to the coastline. So therefore, if we look at the feasible locations in terms of the Indian scenario, the floating and fixed system, just we are trying to demarcate the system in terms of the water depth. So we have considered like a boundary of 50 meter water depth. So beyond 50 meter, the possibility of floating offshore, and near the coastline, we can consider the bottom fixed structures. Same is the scenario for Tamil Nadu coast, where the deep ocean is coming much early. So the feasibility of floating offshore is more promising. So if you look at the design criteria is totally different. So it is not a regular structure. So if you look at the different possible modes of vibration, that means when the structure is deployed, it's a floating system. So therefore, it can rotate, it can have a vertical vibration, it can have a lateral vibration. So we have different type of modes of vibration, that is pitch and roll are basically the rotational modes of vibration. Heave is the vertical vibration. Sway and surge is the lateral modes of vibration. And the code, with different codal provisions, they have stipulated certain standard guidelines, like the tower tilt, the limiting value is around 5 to 10 degree. So those are basically the design criteria. So when we design such kind of structures, we need to look at all those aspects. Like we need to make those structures such that the any response should not exceed that values. So I'll just quickly go through the loads on offshore wind turbine. So if you talk about the Metocean like data, so based on the Metocean data, that is wind and wave data, we can analyze the wind like forces acting on the structure. So I will not go into the much detail of this particular calculation. So many reference papers are available. You can go through it because the time is very limited, so we cannot go through all those details. How do we calculate those loads calculation? The wave load, mostly the drag load as well as the inertia load will come into picture. So we have different wave equations, wave calculation equations are available, considering different type of sea state. And if you look at the stability of the floating system, it's a very simple concept. Like when the metacentric metacentric height is positive, so it is basically considered as a stable equilibrium, and when it is negative, it is an unstable equilibrium. This is a simple floating system stability. So if you look at this small interesting video, you can see how the spar type of foundation is balanced using the this kind of philosophy.
That completely changes. So it's getting a bit more stable, but not super stable. Now when you add something heavier, like these stones, for example, you can aid the
So it is just like a ballast. And considering this ballast, basically we are taking the gravity, the center of gravity is much below, so that it will give more stability. So this experiment is a very interesting experiment. You can see how the stability is
This one is stabilized by ballast, just like
checked.
any more sparse system. The semi-submersibles are stabilized by width and water.
So this is a typical semi-submersible type of foundation. So this is the floating system, and this is a semi-submersible system. So I'll just quickly go through how this is modeled using simple numerical model. And this is a typical numerical system of the TLP type of foundations. Now, coming to the different numerical methods, so basically this kind of structure, since it is a hydrodynamic force and hydrostatic force are acting on this particular structure along with the environmental loading, but mostly those structures are also deployed in seismically active areas. So very little studies are available for this kind of structure, the seismic response, like how this structure will perform under seismic loading. And very few literature available at this moment. So we try to find the response of this kind of system using simple abacus numerical, in the numerical model using abacus. So here the major challenge of this type of structure, how do we model numerically? So normally what we do, we use the CFD modeling, the computational fluid dynamics modeling, and which is very what you can say, it is a very computationally expensive. And also the modeling of soil structure interaction is also challenging in such kind of analysis, like CFD analysis. So we try to use a simple numerical model, and we also verified the numerical model is working properly, but of course it has some limitations. Like this type of structures, we have 6 degrees of freedom, 3 the translatory motion and the 3 rotational motions. So all these motions, when the structure is vibrating in a floating, as a floating system, so we need to consider all different type of motions. Now, how do we incorporate this? See, basically for this kind of system, we need to consider these the hydrostatic forces. That means when it is displaced by some amount, it has some restoring force. At the same time, we have a hydrodynamic force as well. So when the body is pushed against the water, it can also produce some kind of resistance. So all these models, all these criteria, we need to take into consideration for the modeling of this type of structures. So how do we model this? So basically the hydrostatic restoring of different modes of vibration, the maybe translatory motion as well as the rotational vibration, it is basically modeled using incorporating the springs. Now how the spring stiffnesses are calculated, that is also challenging. So it depends on the metacentric height, it depends on the the density of the fluid and depends on the type of structure. And at the same time, when we model this kind of structure, when the system is displaced, like when the structure is moving, it is also pushing the water. So that resistance is modeled using some mass. It is basically it's a point mass which is incorporated at different degrees of motion. So it is very difficult to explain with a more detail regarding this modeling concept. So if you look at this simple diagram, you can, I hope you can understand this. So these rotational springs are basically the hydrostatic restoring forces, and which is incorporated in terms of the rotational springs. And those spring stiffness are calculated based on the various important parameters which are related to the geometric property of the structure as well as the properties of the fluid. So the first one is for the heave motion, and the other two motions are for the pitch and rolling motion. That means the rotational motion. And the remaining other system, like the tower and the blades and other generator system, it is modeled as a lumped mass system, and the tower is modeled as a beam element. So it is basically a very complex model. And of course, if we model in CFD kind of software, so it is basically it's a very computationally expensive. But we try to model using a simple method, so that we can reduce the computational effort. Another interesting part is the mooring line. So basically all the floaters are connected with the mooring system. So mooring systems are basically the cables which are connected with the anchor with the marine soil. And those mooring systems are also having different types. One is a catenary mooring type, another is a taut mooring type. So catenary mooring types are more flexible moorings. As you have seen, the 3 mooring systems are connected with the structure. The modeling of the mooring line is also challenging. So at present, the beam element are available. Say, suppose those who are doing the numerical model, they will understand this. So the modeling of the mooring lines are very flexible system. So there is a lot of challenge for modeling this kind of structure. So what we have used a quad. So basically, you need to first design. You have to first find the coordinates of the catenary mooring line using this equation. Then you have to use the wire elements in the abacus, and a typical is a very novel element which is developed, which is a quadratic hybrid beam element. It's a 3-noded element. Each node is having 6 degrees of freedom, and it has a very high axial stiffness as compared to the bending stiffness, so that it can incorporate the flexibility effect of the mooring line. So using this concept, the system is basically modeled. But many other complexities are there which I am not discussing right now because of the time limitations. So more details are available in our paper, which will be published in the proceedings. So in modeling of TLPs is totally different from other two systems. In TLPs, basically the tendons are under pretension. So because it is basically under buoyant force, and all the tendons are under tensile forces. So therefore, truss elements will be sufficient enough to model such kind of system, and remaining other structures can be used as a beam element and the regular elements. And at the same time, hydrostatic springs, dampers, those can be incorporated. So this is a typical numerical model, and this is a typical model for the semi-submersible type of system. Now, if you look at the validation, so we tried to validate using the natural frequencies of different modes of vibration. So these are the frequencies based on our analysis and the reported frequencies in literature, and which is matching quite well for 2 different type of systems like semi-submersible as well as for the spar. TLPs I have not presented here. And if you look at the animation for different modes of vibration, so these are the heave modes of vibration, pitch and rolling frequencies based on the modeling concept that we have adopted here. At the same time, okay, I think it is taking time. It's not changing. Yeah. So these are the mode shapes for the semi-submersible type of foundations at different modes of vibrations. This is a rolling, sway, and yaw mode of vibration. Yeah, so just I'll finish within 2 minutes. So modeling of anchor is also another important challenge. So we can have different type of anchoring system. This is basically an anchor which is a Cation kind of anchor, or it's a pile kind of anchor. So which can be modeled also using a very simple modeling method. Either you can model using a spring-based method like a beam on elastic foundation approach, or beam on nonlinear Winkler foundation model, or a three-dimensional model. So this is a typical model that has been adopted. So that means three-dimensional continuous anchoring system and the overall system. It is a complete modeling system we have done. And then for seismic analysis, we can apply the seismic loading at the base as a compliant base, and we can see the overall behavior of the system. And in case of anchoring system, there's one important thing that I would like to mention. Say like for seismically active areas, liquefaction could be a major issue. So due to liquefaction, the anchor pull-out capacity may be reduced, and that has also been studied, but that is not included here. So this is a typical response. If you see the relative vulnerability of the spar, semi-submersible, and TLPs in terms of the acceleration response due to the seismic motion, the TLPs are more vulnerable than any other type of foundation because of the flexibility of the mooring line. So the seismic forces cannot be transmitted to the superstructure in case of spar type of foundation, spar type of structure, and the semi-submersible substructure, because those are the connected with the catenary mooring line. But in case of TLPs, those are the pre-tension cables, so seismic forces can be easily transferred, just in a simple term. So that's why you can see the responses are more in case of, it's basically vertical response. So we have done the multi-directional seismic analysis. So the vertical response is quite high, significantly high in case of TLP as compared to the semi-submersible and spar because of the flexibility of the cable. And the seismic fragility analysis is also done for 3 different type of structures, and especially since the TLPs are more vulnerable to the seismic loading, we've also tried to explore the vulnerability assessment at different water depth. So it has been seen that at higher water depth, it is relatively less vulnerable as compared to the shallow water depth for TLP structure. And at the same time, we have also compared with the jacket structure, which are grounded structure, that bottom fixed structures. So if you look at the relative vulnerability, the TLPs are more vulnerable than the jackets are more vulnerable than the TLP, because the grounded systems are more vulnerable to seismic loading. So this is a typical animation. If we compare 4 different type of system, and the semi-submersible, spar, and the TLPs, we compared with the jacket system, and if you see the response, whether it is animating or not, so it is a nice. I think it is not working. So you can see the response of the system. I think the animation has some problem. Anyway, so it is not playing. Some issues are there. Anyway, so just I'd like to conclude here with this, response analysis. What we have seen, the floating offshore can be a game changer, especially in seismically active areas. And what we have observed that the TLPs are vulnerable as compared to the other floating system, right? So, so basically, it can be a promising alternative to the grounded system, and India has to explore the possibilities of this kind of structures in future. So with this, I would like to conclude here, and these are the 2 workshops that are going to come in IIT Bhubaneswar. So if you are interested, you can register for this conference. One is the workshop on the hydraulic barrier and the system using geosynthetics, which is going to happen on 11th and 12th November at IIT Bhubaneswar, and another is a Plaxis workshop. It is a hand-on experience, and 3 days workshop that we are organizing with in association with the Bentley, and where we'll demonstrate the new software. Mostly it is used for the offshore structures like SACS and as well as the Plaxis. Both will be discussed here. Thank you. Yeah. So if you have any question, you can.
Feasible for mostly western coast of India and probably Tamil Nadu.
Yeah.
And in another slide, you represented this color coding like for cost.
Yeah, yeah.
So the western coast shown red while the eastern coast was. So I just wanted to understand how it works and what is the
Yeah, so basically it is a reported data that I have presented here. I think, this one probably.
Yeah.
We're talking about this
Correct,
particular
correct.
case. Yeah, so basically it is considered the cost of the energy for the entire lifespan of the wind turbine, considering all the deploying cost, decommissioning cost. So when the wind turbine is installed, decommissioning is also another important thing. Like after 30 years of design life, you have to decommission it.
Correct.
So because these all components are basically recyclable. So considering all those things, if you see the Indian scenario, I think it's not coming. Yeah. So this part is explored. Of course, it's maybe it is just a preliminary figure. It is developed by some other country. It's not developed by India.
I see. Okay.
Yeah. So it has to be explored. Some feasibility study, of course, further study need to be done. It is not the final figure. So mostly what we have observed at the eastern side, the feasibility of the floating offshore is more because the continental shelf is very narrow. But in the Bombay High and the western side coast, the continental shelf is quite large. Yeah.
Okay.
So the deep water will be coming after a lot of, it will be away from the land. So that's why the Indian government presently looking into the bottom fixed type foundations in Ahmedabad, like in Gujarat and Tamil Nadu.
Thank you.
Okay, thank you.
Any other questions?
Thank you very much, sir, for your very good presentation. And the topic is indeed very interesting because in one of the lectures I was hearing that world is dependent still more than 81% on non-renewable sources of energy. So exploring this is really good in interest of Earth. So I'll call now the first paper of this particular session, which is about torsional dynamic response of offshore wind turbine suction caisson foundations, which the paper is by Mr. Mir Sahib and Bipin Kumar Gupta. And you are, sir? You are presenting, right? Yes. You are? Mr. Gupta will be presenting that. Mr. Gupta, you will have 9 minutes to present, sir, please. Thank you. So can I?
Yeah. So good afternoon, everyone. So I'm here to present this particular paper, torsional dynamic response of offshore wind turbine suction caisson foundations. So there are a couple of authors. One of my PhD student is working on this particular topic, and then I am Bipin Gupta. So in this particular figure, you can clearly see that you have an offshore wind turbine. Recently, a lecture was given on offshore wind turbines. So offshore wind turbines have various types of foundations. So one of the foundation type is suction caisson. And obviously this suction caisson that you see over here is basically an inverted bucket. Okay, and it can have various dimensions and various slenderness ratio, which is basically the ratio of the length and radius of the caisson. Now here you also see that you have a torsional load, which is not very much well explored in the literature. Usually when you talk about offshore wind turbines, you usually talk about lateral loads, force and applied moments. So this particular paper that we wrote was basically on torsion of offshore wind turbines and focused towards caisson foundations. So what are the sources of torsional load on offshore wind turbine structure? So you have this offshore wind turbine structure. Obviously, you know that it's an offshore environment, so aerodynamic loading will be quite huge, particularly during cyclonic events. So you have a cyclone over here, and this aerodynamic loading is basically coming from the cyclone, and you see that turbulent wind excitation on blades and tower can generate torsional loads. Then you have the machinery, the working components within the hub of the offshore wind turbine, and those machinery can generate torsional vibration. And obviously those things will be transferred to the foundation. Then obviously during cyclonic events, you will have hydrodynamic loading, and if somebody has studied fluid dynamics or fluid mechanics, he must be aware that there are eddy currents and various kinds of mechanisms that might come into play which might generate torsional loads. Apart from this, another major event that can be there is basically these wind turbines are installed in pretty colder areas, Baltic Sea, North Sea, where icebergs or ice sheets are quite frequent, and there could be accidental collisions from boats or any ships passing by ships, which can generate torsional loads. And all these forms of loading in torsional form is basically transferred to this particular foundation, and the foundation has to resist it. Foundation basically means this particular caisson and the soil. And suction caisson, these are basically installed in water depths of 35 to 60 meter, which Professor Haldar already talked about. Also, these torsional loads are dynamic in nature. Okay. So we are going to look into one of the design requirement. So one of the design requirement for offshore wind turbine foundation is predicting the natural frequency of this offshore wind turbine structure. Okay. Now, because the loading is dynamic, so one of the things that you need is the torsional dynamic stiffness at this particular level, so that you don't really have to do an integrated analysis of the entire system. So if you can give, if as geotechnical engineers we can give the torsional dynamic stiffness at this level, so a structural engineer probably can do the natural frequency calculation. Okay. So what is there? Basically, this caisson and soil can be modeled as a spring dashpot system, and this spring dashpot system is nothing but a complex dynamic foundation head stiffness at this particular level. Now, if we look into the geotechnical literature, not much is done on this aspect of natural frequency calculation. So we are going to develop a model which will basically account for the torsional load, and from the model, from the solutions from the model, you can obtain the torsional dynamic stiffness at this particular level. So we're going to talk about the model. So this is a developed analysis. So you can see that I have a caisson foundation. I'm ignoring the cap for now. And then it is obviously embedded in the soil. The caisson has a length LP and it has a radius RP, and obviously it has a thickness which is TP. Then the soil is homogeneous, and properties of it is our shear modulus. Because this is a torsion load, so you usually take into account the shear modulus of soil. Dynamic, so density is coming into picture as well, because inertia effects will be there. And then you have this material damping ratio of soil. And the properties of suction caisson are also given, which is basically the shear modulus of the caisson, which is denoted at GP. And then obviously the inertia effects of the caisson will also be there in case of dynamic load. So you have rho P. So now you have a torsional load applied on top, and then obviously you see that this is the length of the caisson foundation, and because of the soil beneath the caisson, there will be another torsional load, that is that torsional resistance that will show up. So that is written as TVT over here. To start with the analysis, the first thing that we do, we follow a displacement-based formulation. So the first thing that we do is assume the displacement u theta for the soil, which is given by this particular expression, in which phi p is basically the twist of the pile, phi is basically a soil displacement function, E j omega t accounts for the dynamic nature of the problem, and rp is basically the radius of the caisson, which balances the dimensions. So with this particular assumption on the soil displacement, I write the strain energy density of soil in terms of this particular equation, in terms of the elasticity theory, following the elasticity theory. So this is the expression that you see, and you see that phi is there, which basically accounts for the soil, phi p is there, which basically accounts for this particular caisson, and then the soil properties and other properties are incorporated. Dynamic problem, I'm applying the extended Hamilton principle, which is given by this equation. And then you have K, pi, and WNC. K is basically the kinetic energy of the entire pile soil system. Pi is the potential energy, and WNC is basically the work done by these two forces, external forces. You can think of it as external forces. This is an external force. So, and all these energies and work done are expressed in terms of this particular equation that we have assumed. So we put all this in this particular equation, apply the variational principle, and arrive at two differential equations. One is the differential equation for the soil domain, in which gamma is basically the rate of decay of soil displacement with increasing radial distance from the caisson soil interface. And this equation is or can be solved using Bessel's functions. And then you have the differential equation for
you have 2 more minutes,
yeah,
please.
I'll complete. So this is the differential equation for the caisson, and in this particular equation is associated with this soil parameters, which is Ks, Ts, and omega s. Ks and Ts makes the problem 2 parameter, unlike Winkler-based model. And then to solve this particular equation, you have these two boundary conditions at the top and base. This is something that you need to notice is that you have T naught B. It is also written in the same spring despot form. And it is taken from some other literature. So we write a MATLAB code with all this and arrive at the solution to the problem. People who work on foundation dynamics, they usually try to calculate the foundation head stiffness, which is given by this particular equation. And in this particular equation, you see that there is this quantity KT and CT, which is nothing but KT is the spring stiffness in the torsional mode, and CT is basically the damping. So we compare our model with an existing framework in the literature, and we end up getting a very good match. I'm not talking about what are the dimensions. So with this particular accuracy that we have arrived at, we have rerun the MATLAB code to do a parametric study, extensive parametric study on Cajun foundations, which is for LP by RP4 and LP by RP10. And you can see that we have obtained results for GP by GS 10, 10 to the power 3, 10 to the power 5, 10 to the power 2, 4, and GP by S 10 to the power 6 and 7. So this is the real part of the stiffness that you have, which is basically the spring part, and this is the damping part that you have, which is basically the C part. Okay, so you can use all these results. I'm not going into the details or the interpretation of the results because we don't have enough time. So this is for LP by RP 10. So this was all on the paper. So summary and conclusions from the paper: an analytical method is developed, and we found that the analytical method is accurate. The analysis method is used to perform an extensive parametric study for suction Cajun foundations. Results obtained can model the Cajun soil system at this particular point, and then as geotechnical engineers or structural engineers, you can use this input from geotechnical engineers to calculate the natural frequency of this offshore wind turbine structure. So this was all from the presentation. Thank you.
Thank you.
Yeah.
Any questions? I think there are no
Thank you.
questions, but
Yeah.
thanks for nice presentation and completing it within time. So next we invite Ravi Shankar Sahu for presenting stability analysis of offshore wind turbine monopiles and hybrid foundations under vertical and lateral loading. You have 9 minutes.
Good afternoon, everyone. I am Ravi Shankar Sahu, PhD scholar, working under the supervision of Dr. Soumya Chawla at IIT ISM Dhanbad. So my paper title is Stability Analysis of Offshore Wind Turbine Monopile and Hybrid Foundation under Vertical and Lateral Loading. These are my presentation outlines. Starting with the introduction. So the world is moving or shifting towards the renewable energy. So we require to reduce greenhouse gases, secure our energy security, and basically I told you what is monopile foundation. It is a long diameter pile which is ranging from 4 to 10 meter and have a L by D ratio ranging from 3 to 10. And the advantage of this is provide strong and stable wind and have no land limitation, environment friendly and cheaper than the fossil fuel. As you can see from the chart that fossil fuels required $93 per megawatt hour, while the offshore wind turbine required only $81 per megawatt. Why do we need expansion? So basically, offshore wind turbine is concentrated in Europe and US, 60% is that. And India and China has long coastal area, and China has already M300 gigawatt by 2050, and India targeted 70 gigawatt by 2030. So challenges of offshore wind turbine is its installation cost is too high, limitation of water depth is limited as monopile is ranging from offshore from 40 meter, and the installation vibration is caused the impact of marine life. So limitation of foundation of which their type is listed here, that gravity has limitation, it required bed preparation. Monopile has water depth limitation, is only go up to the 40 meter. Tripod had high cost, and jacket had installation ka floating has a limitation that is may get unstable. The failure mode of offshore wind turbine foundation is an ultimate limit state. There is a structural or soil collapse, and the symptoms is buckling of soil failure, and serviceability limit excess. It get excessive deformation, and tilt and displacement is the systems. And for fatigue limit state, the crack of materials failure occurs. And loading on offshore wind turbine are static loading, which is self-weight, aerodynamic, that is wind load, hydrodynamic, and operation and control loading. While we install that, there is a impact load on there, that is the operational and control load, and miscellaneous forces are like earthquake, tsunamis, wake, and sometimes ship impact. Based on the literature, previous literature reviews, we have some few research gap, like most strategy focus on conventional monopile or small scale helical pile, not on helical monopile offshore wind foundation. Further, there is a limited work on vertical and lateral loading on soft marine clay, and lack of detailed understanding of helix geometry influence on load bearing capacity, stress distribution, and deformation. So based on that, we have two objectives, that is symmetrically simulated and compare diameter configuration, determine their effect on overall foundation strength, and another one is to evaluate the influence of helix diameter on the load bearing capacity performance of monopile in offshore condition. So methodology is soil sampling and characterization, numerical modeling in finite element discretization, load applied on monopile and helical monopile. Coming to the profile properties of soil, that it referred directly from the Chang et al. 2022, marine clay sourced from offshore site near Shanghai city, China. So numerical analysis. Conventional monopile conducted a 3 finite element analysis using Midas GTS NX. Monopile have 4 meter diameter, embedded length is 35 meter with 1 meter exposed above the seabed. Monopile treated as a linear elastic structure. Material properties are following, and wall thickness of pile is determined using API empirical equation. Coming to the soil model was taken as Moore-Coulomb constitutive model for marine clay, and soil domain is verified through sensitivity check, and large soil domain as we eliminated the boundary effect, and refined mesh is a 96,000 total element validated by convergence study. Coming to the helical pile, helix to shaft diameter is taken as 1.5 meter, pitch is 1/3 of the helix diameter, and helix thickness is 150 mm. And coming to the result and discussion for the vertical load response, as you see on figure 7, monopile exhibit a clear transition from elastic to plastic behavior, reaching a failure state at approximately 0.5 meter. And from figure 8, helical pile showed a superior response with a stiffer initial reaction, transition to plastic at higher displacement of 0.6 meter, and higher ultimate load capacity and reduced deformation under the same load in helical pile. As you can see from the figure 9, I have compared the result with Dai et al. 2022. Coming to the lateral load response, both files showed initial elastic behavior followed by a transition to plastic deformation. The helical pile demonstrated a stiffer response, delaying the onset of non-linearity unit a higher load. Yield transition occur at 0.3 meter for the helical piles and 0.175 meter for the monopile. So soil reaches plastic ferrule state at 0.6 meter for the helical pile and while 0.4 meter for the monopile. And both the results are compared with the Dye et al. 2022. Coming to the conclusion and summary, helical fins significantly enhance monopile performance in soft marine clay under both vertical and lateral loading. And vertically, the helical pile provides significant improvement, increasing bearing capacity by 20% and reducing settlement by 30%. And lateral direction load, the helical configuration also delivers superior performance, boosting capacity by 12.5% and reducing displacement by 21.6% for a much stiffer response. So the conclusion is this result confirms that geometric optimization through helical fins is a highly effective strategy for developing more efficient and resilient monopile foundation for offshore wind turbine. So these are the references of these studies. Thank you.
Any questions? I just wanted to ask, the monopile you modeled,
Yes.
so you consider helix only at the bottom, right?
Bottom, yes.
And what kind of material for that pile you consider, whether it's concrete?
Steel, sir.
Steel.
No, steel.
Okay, so it is like a driven pile.
Yes, in monopile it is a driven pile, but while applying a helix, it should be a rotatory one.
Yeah, so that is my question. How do they install such pile? Whether you need to like screw it or?
Sir, it is starting one, like it may be further that in rotating one is developed. Actually, I just started on helical pile, so
Okay.
it is not currently not in a
Okay.
position through.
Thank you. So next we would like to invite Syed Bakar Mehndi, for presenting measurement of pipe soil interface friction at low normal stress using a modified direct shear machine.
So, good afternoon everyone. My name is Syed Bakar Mehndi and I am a research scholar at IIT Bombay working with Professor Shantiram Chatterjee. So, today I will present the preliminary study of my research work entitling as Measurement of Pipe Soil Interface Friction at Low Normal Stress using a modified direct shear machine. So, though we are talking about sustainability, green energy and renewable energy, but from the graph presented by American Petroleum Institute, it can be seen that our demand and consumption of petroleum is not reducing. So, which is forcing the industry to explore more towards deeper water. So, if we are moving towards deeper water, it is required to lay pipelines, and most of the deep water pipelines are surface laid. So the major challenge is to bring the extracted crude from the deep waters to the processing unit. So we all know that crude product contains wax. So due to ambient temperature and bringing from extracted unit to processing unit, it may solidify, and which will fail the whole system of the flow. So for that we need to heat up the pipeline. So as we know that these pipelines are made of metal. So with increase in temperature, the pipeline tries to expand. But as it is surface laid, the soil will resist the expansion, and due to this, axial stress will come into the soil. So due to this axial stress, change in temperature, axial stress will come into the pipeline, and the pipeline will fail in 3 modes, which will be pipeline walking, which is very critical at the end, and maybe at subsequent part of the pipeline lateral buckling may happen, or critical and upheaval buckling may happen. So initially, what kind of stress will come in on the pipeline, it is required to study the axial pipe soil interaction. So to study the pipeline interface friction, there are 5 kinds of instruments available, like which is tilt table, ring shear, interface shear box, cam shear, and cam torque. So since we know that pipeline is not a load bearing structure, so the load which is coming on the soil is around 10 kPa. So at 10 kPa, they like most of the direct shear machine or shear machine works on very high stress. So it was a challenge for us to modify the direct shear machine to operate at low normal stress, because the load cell we mostly use captures high stress. So this is the computer operated direct shear machine which we have used. So in the direct shear machine, the load which is coming, the normal stress which is coming on the soil sample is through stepper motor based feedback mechanism, because as we know that if there is a motor based system, there will be a fluctuation of loading. But for low normal stress, it is a challenge, because if you are working at 100 kPa stress, the fluctuation of 1 or 2 kPa is accepted. But if you are working at 8, 9 kPa or 10 kPa, then fluctuation of 1 kPa or 2 kPa will hamper the result, which will create error. So we removed that system and we applied gravity based load system to apply the low normal stress. So we took the soil which we brought from Vashi, which is an area in Mumbai. So and after conducting the preliminary test, we found that it is a silt, so whose properties are given like specific gravity as 2.62 and all other parameters like liquid limit 85% and plastic limit 51% and CV value as 1.1 meter square per year. So with that soil, we chose mild steel as our interface material, and we all know that with drainage characteristic, we can quantify that the shear behavior will be as drained or undrained. So it is required to incorporate dimensionless velocity, which is already like used for CPT based, but there is no data for direct shear test or interface shear test. So we use this dimensionless velocity, and with these dimensionless velocity number, we can say that the shearing will behave as a drained or undrained case. So this is the typical result of the test which we have conducted at shearing rate of 0.1, 0.5, 1, 2 and 3 mm per minute with low normal stress of 7.24 kPa and 9.66 kPa. So the residual shear stress ratio is coming like that. So we used the residual shear stress ratio to fit in an equation which is a backbone curve. The upper part of the backbone curve will show the drained behavior and the lower part of the curve will show the undrained behavior, and in between transition we can represent as a partially drained behavior. So we also try to fit the drained behavior into a power law, which is tau d is equals to A into sigma n to the power b. Here sigma n is the effective stress which we are applying on the soil. So in the drained case it will be same. So but for the undrained case, that will be reduced at as excess pore water pressure will generate.
You have 2 more minutes.
Okay, I'll finish. Next one is the last slide. So with that equation, we can back calculate the excess pore water pressure which will come in the soil, which will come in the interface while shearing. So we fitted that our results in the equation, and the results are here. So for when the soil interface was behaving as undrained, the excess pore water pressure was 1.69 and 3.87 kPa. So in summary, I would say that we have modified automatic direct shear machine to be operated as interface shear machine at low normal stress. We performed a test, and we fitted our results in an equation so that we can characterize the results as drained and undrained behavior. We correlated our drained results, and from the undrained equation we back calculated the excess pore water pressure which may come. And as all we are talking about offshore, so for Indian environment we need more soil data, so that in future if any kind of project will come, we'll have the soil results. So like we are using AI and modeling, AI and ML, so we need data for that. So it was a great experience here. So I enjoyed a lot in the conference, and learned a lot also. So with a heavy heart, I would say thank you.
Questions? Thanks for a nice presentation. Yeah. So with that, we'll move to next presentation, response of buried pipelines under impact loads from dropped objects. Mr. Yeah. Avikal? Okay, Abhishek Ghosh. Okay. Welcome. So you have 9 minutes.
Good afternoon, everyone. I am Abhishek Ghosh. I am currently working as an assistant professor at IIT Kharagpur. So this is a work, part of the master's thesis of my student Avikal Srivastava. So I am presenting on his behalf. So this is this is focused on finding response of buried pipelines under impact loads from dropped objects. So as you can see from this particular figure as well. So this is a field figure that I've got from PhD thesis, which happened like how the pipe has deformed under the impact with an anchor. So our study is to understand such response of pipe, but in buried case. So if I try to represent this in a schematic presentation, so in this case, so we know pipeline acts as a lifeline or a artery. We often refer it as of the offshore infrastructure systems, particularly because of its nature to safely transport, storage, and supply hydrocarbons. So obviously the stability and longevity of the pipelines is of immense importance while going for an offshore projects itself. So in that case, so suppose during a construction or a installation or certain operation of a offshore platform, in accidents, if an object of different shapes, if it drops from the top, it can go through the water or hit the soil bed as well as penetrate and hit eventually the buried pipes itself. So such kind of situation can create damage in the pipelines. A similar scenario that I will show, so it's like a vessel. If the pipe networks is within the anchorage zone of ships, so even in that case, anchor can drop in accident. It can hit the pipelines and cause damage there. So now these kind of impact loads can cause a damage and rupture of pipelines, which can cause which has an environmental hazard part where your oils and hydrocarbon leaks into the water and contaminates the ocean itself, as well as these pipelines, if it's particularly buried, the rehabilitation of such damage takes a longer time to do. To detection and rehabilitation of damage, it's a longer time to achieve, and it's an economical target as well. So the economic part has also needs to be taken into account. So there were some studies in the close to 2000s by UK health and safety executives as well as International American Gas Associations. So where they found out that 40% of pipeline failures were caused because of these external impacts. Now DNV guideline, this particular DNV RPF 107, this specific code is actually for pipeline protection or risk assessment part. So in that code also they considered, developed a risk assessment model, or people are working on this risk assessment model where they try to understand how much the damage such external impact can induce in a pipeline as well. So now people have done number of researches on these particular cases, but the majority of these researches that we have found is on a pipeline which is exposed, or like it simulates an on-bottom pipelines itself. So where the object is directly dropping on the pipes itself. So there are laboratory experiments provide risk assessment, but there are limited study, very limited studies on the nature of how the buried pipeline would react to such impacts. So in that situation, the major difficulty is to track the movement of the object through the soil, as well as try to simulate the impact that will cause with the pipe itself, and obviously to understand the impact of different parameters on this particular study. So now, as this is a very fast penetration problem, the major challenge is to track the movement of this particular object through soils as it hits the pipe and creates a dent in the pipe itself. So it's a large deformation problem numerically to solve. So obviously the distortion of meshes needs to be taken into account. It's a high-speed penetration problem for such aspects of inertial resistances and other aspects needs to be taken into account, and as well as after that the impact that also needs to be accurately simulated. Now for that case, we try to use coupled Aurelian Lagrangian technique. Now if I give you a very briefly, if I talk about this, so there are two types of bodies that has been used, or two types of parts that has been used in this particular part. One that involves the Lagrangian part, which is the ball and the pipe, where it deforms the nodes that are formed there. So these mesh displacements follows the material displacement. It's like they are stitched together. But whereas in case of an Eulerian mesh, the material can flow through a spatially fixed domain, and as it flows through a spatially fixed domain, all the material parameters are mapped at every increments. So it avoids having any kind of mesh distortion, as well as it provide more accurate results. So this is specifically useful to track the soil flow, how the soil flow can happen when the object is going through the soil and eventually hitting the pipe. Now, this generally is done using a dynamic explicit scheme, so which is where we use such scheme. When we use such scheme, it's become very dependent on the time step that we chose, because it follows a direct integration process, and the step time is eventually becomes a function of the mesh itself. So the mesh convergence study that we have to do is to ensure that the results that are stable in a sense, with the change of the mesh, we won't observe any kind of significant difference in the deformation of the pipeline. Now also there is another aspect that needs to be decided while doing this study, is the range of erupted velocities. Now we have applied an impact velocity on the object at the point of so the movement of the object through the water has not been modeled. So rather it has been associated with an impact velocity. So obviously how much is the impact velocity, that needs to be taken into account, because we have to understand this object will fall through the water, so it will eventually reach a terminal velocity. So we have to calculate the terminal velocity, and based on that we can calculate the impact, we can choose the impact velocities. Now these are the material properties. I'll not go into detail of each properties. Just the red ones are the ones which we varied to understand the effect of each of these parameters on the deformation of the pipelines. Okay. Now, if I try to explain it, like again, this whole process, it's like, so generally this height of the fall, that's through water, that has been modeled with the help of a impact velocity. So obviously, when the object is at the point of contact with the soil, so it brings a certain level of kinetic energy as well. And the velocity is actually, as it moves through the soil, the velocity decreases as it decelerates, and eventually when it hits the soil, it creates a local deformation at the pipeline itself. So this deformation can have a 3 different dimensions. It has its lateral spreads as well as its depth. So the generally, according to the codal guidelines as well, this dent depth has been, which is the movement of the damage of the pipe at a certain point with its original position, that has been considered as the damage parameter or damage assessment parameter itself. So that we are trying to track with the changes in the velocities. So this is the soil deformation in 2 specific cases. As you can see from here, this is for the sphere drop and this is for the conical drop. Obviously from the cavity that has been formed because of the this object movement is also a bit different due to the nature and the sharpness of the frontal part. So, and also you can see, so these, when it moves through the soil, you have to understand this shear resistance as well as inertial resistance. There are other resistance as well, but these 2 are the major factor that plays a role as it moves through the soil, that has been taken into account in this study. And then you can see a gray part at the bottom which shows the exposed pipeline part. So it eventually gets to hit the pipeline. So why, another part, why is important for this study? Now when we are doing this study on an exposed pipeline, we already are aware about what velocity in which it's going to hit the soil. But when it's buried in the soil, it needs to track the movement of the pipe, object through the soil accurately. Then only we'll be able to capture the exact velocity at which it will impact the soil, impact the pipe. Now these are the deformation of the pipelines. Now these are for the cone and the sphere. As you can see, the conical has a more concentrated deformation contours. So if I see the longitude,
You have already crossed the time, so please wind up in next 1 minute. Okay. It's already 10 minutes. So
okay.
Because it was interesting, I didn't stop you in between.
Okay.
Thank you.
I'll stop. So I'll conclude in 1 minute. Okay. So this is the dent depth that has been developed here. So this is a longitudinal deformation, as you can see, and this is the cross-sectional view. I have already discussed the dent depth that can be calculated. So this is the we track the movement deformation at all the points across the circumferential pipe. Now, I'll just quickly go over with the parametric part. So these are the different effect of different properties. One is the mass of the objects. As you can see, the velocity, gradual velocity decrease is gets very fast as we hit the pipe. So this is the velocity of the object, how it changes with that. And when we change the shear strength, obviously there is a decrease in the dent depth as well. And finally, the burial depth itself, as we can see, 1 inch at 1 diameter depth, we get to see a drastic decrease, but there is a gradual decrease here. It means it has yet to reach the pipe itself. So the burial depth plays a huge role here. So that's what we can understand from this study on a brief level, is that the coupled Lorentzian technique is a suitable technique to kind of simulate the movement of an object through the soil and its impact with the pipelines. And then we studied the different parameters on the dent depth as well. Thank you for your time.
Thank you for the nice presentation. Any questions? No, thank you.
Thank you.
So next we would like to invite BP Naik for presenting unconfined compression strength of bentonite based backfill materials.
Good afternoon all. Myself Banavat Prasad Nayak, a research scholar from IIT Patna, working under the supervision of Ramakrishna Bhag. So my research topic is on thermohydromechanical behavior of buffer or backfill materials in deep geological repositories and application to isolate hazardous high-level radioactive waste. So in that, one of the parameter need to be studied is unconfined compressive strength. So coming to the talk, so coming to the introduction. So nowadays the production of electricity is increasing due to the demand. So the major source of electricity is hydrothermal and nuclear power plant are the major source of electricity. So up to now India has 24 operational nuclear power plants. So with the total installed capacity of 8,180 megawatts. So during this production of this electricity, some amount of radioactive waste is generated. So mainly the most dangerous radioactive waste is high level, like during the production, like low level, intermediate level and high level waste will be generated. Depending upon the toxicity, they are categorized into low, medium and high level. So low and intermediate level waste are okay, like they will not create that huge impact, but high level waste are very dangerous. They should be disposed of properly. So high level is the most concerning because it contains a much higher concentration of dangerous radionuclides, and HLV means high level waste remains radioactive for hundreds to thousands of years. So requires careful handling and isolation from environment to reduce risk over the time. So if it is not managed properly, you can see the incident that has happened in Chernobyl disaster incident. In 1984, a series of explosions destroyed Chernobyl nuclear reactors, and the fire burned for 10 days and expelled more than 50 tons of radioactive waste rapidly. So even today, a large portion of land is considered as uninhabitable. So we can have a, so you can see, oh sorry. So you can see that the Chernobyl disaster incident, like photograph of reactor number 4, has damage due to the explosion. So young victims. Okay. So this is an affected young victim, and even it can change the genetic of our humans or any living being. Like you can see, this is the pig actually having different shape. So that is the impact of high level waste if it get exposed to living organisms or human beings or whatever it may be. So it has to be managed very properly. So depending upon the toxicity, like low, intermediate and high level radioactive waste, so they are disposed in near surface facilities and deep geological repositories. If they are lower level and intermediate level waste, they can be disposed in near surface facilities, like they are storing in some containers, and they will be disposed in some below 30 meters depth. And other one is high level waste. So these are very dangerous. So this will be disposed in the range of 300 to 1,000 meters depth. So those constructions are called deep geological repositories. So my topic is related to deep geological repositories. So in these deep geological repositories, you can see the schematic of schematic representation of the deep geological repository. The first one is, so this is radioactive waste will be stored in some containers. Those containers are called canisters. Okay, so those canisters are disposed in some rock structures. So in rock they will make some rooms. In that room, these containers will be stored. So the rocks between rock and these containers, some space is allowed because to have a layer around to that which is acting as a buffer material. So generally, the bentonite is used as a buffer material because of its high swelling nature and low permeability. Because if in future, in case these containers may get corrode or it may get compressed, the radioactive tries to come outside. So in order to retard that flow and to reduce the water flow also from outside, so we can just we can have a schematic representation. So at center, this is radioactive matter, and this bentonite is compacted and it will layer in layers. So next to this rock. So if you assume the real condition in the field, so from one end the water is coming, there is a chance of coming water flow inflow, because when constructing those rooms there is a chances of faults happening or some earthquake movements in the future also, because this needs to be disposed, and this is a permanent sealant, like it has to be sustained more than thousands of years, because the activity of radioactive is more than, like, it is increasing cycle, like today till next night it is a like chain reaction, so it has to be stored more than thousands of years. So if you look at the field conditions, from one end the water is coming inside, from the center the heat is coming, heat is generated from this radioactive waste. So in these two conditions, how this bentonite is behaving, like it is like some part it is saturated, some part it is unsaturated, some part it is completely dry. So we need to study that condition. Like as a geotechnical engineering, I am not dealing any radioactive waste. Like we are not going to touch any radioactive waste in the laboratory. We just, in place of radioactive waste, we are just giving heat. So this, if you see the cross-sectional view, from one end the heat is generating, from other end the water is coming. So under this coupled condition, like see heat and water. So the coupled condition, so thermo-hydromechanical behavior, the topic name as thermal THM behavior. We can short this THM behavior of bentonite. So bentonite has been valued as a promising buffer material. So whatever the material that is, it is shown here is bentonite clay has been valued as a promising buffer candidate due to its high swelling nature, low hydraulic conductivity, and good mechanical performance. So but one of the major drawback of bentonite is it is having low thermal conductivity. So if the thermal conductivity is low, the heat flow is not uniform, and its rate of heat flow is very less. So it is mixed with the sand and graphite, or having higher thermal conductivity material. Okay, sir. So I will just conclude. So the adequate property of temperature should be below 100 degrees, because if it is more than 100 degrees, the material property will be changing, bentonite properties will be changing. If the material property is changing, then the design parameter, everything will be changed, and the thermal conductivity should be in the range of 2.4, because to have a good efficiency flow in the heat, and the hydraulic conductivity should be in greater than 10 power minus 12 meter per second, and swelling pressure should be 1 ampere. These all 4 parameters we are dealing in. This is my research topic. So one of other parameter I want to study is unconfident compressive strength. So today I am going to show how the unconfident compressive strength has changed with the change in temperature or water content, any field condition. So we can see the look or disposition of buffer material. So in place of radioactive waste, this hole, like before and after installation of heater. So this gravel is bentonite, it compacted in block, and it has layer in layer. So it is sourced from the Villa Retail in 2008. So these are the materials we have procured. So bentonite is procured from the Rajasthan, from alkali mines. So this is bentonite, sir.
You have 1 more minute, please. Kindly wind up.
Okay, this is the basic properties of bentonite, and this is a graphite powder, PPF, and sand as selected as additive material. So before these are the additive materials, so we need to select what combination we are going to use. So to select the combination like additive contents in the bentonite mix, we have done many tests like swelling pressure, thermal conductivity, string stress. So I am going to show you one parameter like thermal conductivity. So with increasing the sand content, thermal conductivity increase. Similarly with the graphite content also, but increasing rate of thermal conductivity is optimum at 27% for sand, and for graphite it is 14%. So based on these two categories, so based on this thermal conductivity parameter, we have selected 2 combination of mixtures. One is bentonite sand and one is bentonite graphite and fiber. The fiber content is fixed to the 0.25%. So when I can show you the preparation of this bentonite sample. So bentonite is mixed with the required amount of water to get various water content, and it was compacted to 1.7 density. So you can see that it is sealed in bag, because as bentonite is very clay, it is pure clay, so it needs some time to get uniformity, like homogeneity. So it was packed in polythene cover, and it was kept in some room for 10 days, and next compaction is processed. Then after removing the compaction, it was sealed with wrapping roll, and this sealed in the steel molds. Next, the results. So as we know that I am saying that you see unconfident compressive strength. So it was unconfident compressive strength test was conducted at different temperatures. The temperature was given by keeping these containers in thermotank. So required temperature like we have given 27 degrees just a room temperature, and 40, 60, and 80. So at different temperature, we have checked what is the weight of the sample in order to get how any changes in the specimen condition. So there is no change, much change in weight of specimen. Only a small amount of around 1 or 1.2 grams was lost. So with this weight loss can be considered as a negligible in terms of the effect on the test results. So with increasing water content, UCSC strength is increasing. Other thing is with increasing temperature also UCS is increasing, but the increase was found to be much effective up to 12%. After 12%, the increase was not that effective. So on comparing these two, bentonite sand mixer has shown temperature effect was.
It's 12 minutes. Please conclude.
So these are the just effect of temperature because the fiber is acting as a reinforced material. So the UCS of fiber reinforced bentonite was more than that. And conclusion are the same. The simple thing is the increase in UCS was found to be significant in specimen with water content up to 12%. And the effect of temperature on UCS is more significant for bentonite sand mixer. And because in bentonite fiber mixer, the uniaxial stress is converted to triaxial condition. So the more it can take more load, and fiber is acting as a bridging effect. So it has given much load, much strength. So this is the acknowledgement. So this was conducted in Department of Civil and Engineering IIT Patna. So I want to gratitude that and some other selected references. Thank you.
Thank you. Any quick questions? Thank you. So we'll move to next presentation by Deepali Anand. Is she here? She's not here? Okay. So next one, Lami Karagos. And the last one is by Kinjal Parmar, microplastic release from Gabion matrices. Okay. Yeah. So you have 9 minutes?
I'll conclude before 9.
Okay. Thank you.
Okay, right. Good afternoon, everyone. I'm Kinjal Parmar. Of course, so far we have seen our research scholar, my fellow presentations, and I'm representing from the industry. And so far we were talked about the different solutions. Now extending it a bit, and we will see some impacts of whatever the different solutions we offer, environmental impact and how it relates to. So basically my topic is evaluation of potential microplastic release from the Gabion matrices and assessing the environmental impact. Now there's a reason behind it why specific this particular topic. We'll see one by one. So the content of my presentation, which covers the basic introduction, the materials we have used for this research, how the tests were performed, and result followed by the conclusion. So let's see some background about the microplastic release. So nowadays, with the increased infrastructure development and industrialization, so there are various adverse effects on the environment. As specifically now growing concern is the microplastic pollutions, because we all are working in the geosynthetic industry and we see how the different solutions are being used. So we have to be mindful about its long-term environmental impact as well. And particularly, if we see about the aquatic ecosystem, such as the rivers, lakes, and oceans. So microplastic particles less than 5 mm in size, basically, that originate from a wide range of sources. It includes the breakdown of larger plastic debris, synthetic textiles, fibers, tear wear particles, personal care products, and so on. And these are the industrial materials. So due to their small size, these particles are easily transported through the stormwater runoff, wastewater discharges, and atmospheric deposition, and so on, ultimately accumulating the aquatic environment. Now, if you see this, the image also, like it explains how the mechanism it works, like starting the source degradation, basically the plastic, textiles, industrial waste backgrounds. Then the pollutant carriers through this microplastic transport harmful chemicals, which goes to the gives us the sustainability advantages, reduction in the material overall cost, even the installation, the speed and everything. And that is why this type of Gibbon mattress is basically with the very high abrasion resistance polymer coating that represents a very sustainable alternative to the traditional methods like the riprap through the individual analysis for the each application. With this I will conclude. Thank you so much.
Thank you. Any questions? So I think both of these case studies were from outside India. So are
Yes,
we
yes.
doing anything in Indian scenario in terms
In
of
Indian,
research?
we have installed and we have cases since many years, but that was river hydraulics. The only point of taking this, because we wanted to take the saltwater exposure, and that is why the coastal projects. But the same thing can be done here also, and can be observed the same.
We have these products here available.
Yeah. We do have the manufacturing here in India only, in Pune, basically. So yeah.
Thank you.
Thank you.
I have a question.
Yes.
You said that you took a project which was 41 years old, okay?
Yeah.
So what were the
42 years of the exposure. Yeah, that I installed.
So what was the initial thicknesses you taken? Because at that time you would not have envisaged this issue. Because these issues are coming very recently, right? So what you have
Right.
measured is 2 days thickness, right?
Yes.
So what were the
So
initial values?
initial thickness, basically all our material we offer 0.5 mm thickness. So if the basic diameter is 2.7, after the coating it will be 3.7. So that is the measurement we take.
That means you have taken a parameter which is not validated.
No, how come it's not? I'm not getting the exact
No,
question.
I'm saying
actually, like
that if I
validated.
have to compare, if I have to calculate the reduction in thickness, I must have 2 values.
Yeah, the initial
which are
one
validated.
and the final one.
So initial value which would have been put at a time which was 42 years ago from today, how to confirm that was the value? This is my point.
No, because
how did you confirm that?
Because we manufacture the same material. That like there is no change in the coating thickness, and all the quality checks before supplying of the material that has been checked. Like that the uniformity in the coating, it does not vary. So the standardization in the manufacturing process is already in place.
Okay, thank you.
Yeah, and because all the materials basically it's a CE certified material, so the quality is ensured that there is no variation in that particular the thickness of the coating.
Thank you. Thank you.
Thank you.
So 2 papers are left, just in case the authors are there, or shall we conclude the session? So if they are not there, then let us conclude the session, right? So just.
Hi. I would like to express my sincere gratitude to Engineer Hemant Manchanda and Engineer Sujan Kulkarni for chairing this session on this called Coastal and Environmental Engineering. And also my heartfelt thanks to Professor Sumanta Halda from IIT Bhubaneswar for delivering a thematic session on the offshore wind turbine. And also would like to extend my appreciation to all the presenters and the audience present here. Now I request Chair and Co-Chair of this session to honor our thematic speaker by giving a token of appreciation.
Good work, sir.
Now, I would like to request Dr. Chaidul Haq Chaudhary from IIT Bhubaneswar, Assistant Professor, and also the award winner of Bright Spark Lecture to honor our chairs for this session. Please. Engineer Heman Manchanta. And I request Engineer Sujan Kulkarni to be. Now I request all who are in this stage to come for a group photo, please.
Thank you. Thank you, everyone. Thank you. Thank you.